So, welcome to the Maths 1B people, and AQMF people, I'll let you know when your bit's finished. So, I'm going to be talking about multivariable calculus today, trying to organise it, and when I finish talking about that, there will be time for you to ask questions about pretty much anything else in Maths 1B, taking into account that I will be talking about something tomorrow which I have forgotten what it was that I was going to do. Cool. Oh, and please, if you are confused about anything I'm saying, do ask, put up your hand or call out and interrupt me up to a point if you want clarification on something. Happened very well in the last seminar. Someone asked something and I'd missed a really quite vital bit of the course. So little star that says David is not responsible if he misses something out. Yeah, that's your job. So I might not cover everything, but if there is something I haven't covered, ask me and I will try and talk that through. Okay, so first, let's talk about multivariable calculus. And the concept of it is it's like one variable calculus, only more. So we're going to need to think about what it means to be functions of multiple variables, which your lecturers have gone into probably quite some depth about. But we're used to this. Function of one variable, something like that. You're used to how that works, and you're used to saying, well, here you've got an x-axis, and here you've got technically an f-axis, and you can draw that function somewhere. I don't know where it is. That's probably wrong, but it's most definitely a parabola that's going upwards. Okay? And so here we have that there's an x value, and this f tells you how far from the x-axis to go in order to find where to draw that dot. All right? So that's functions of one variable. And we're fairly used to how functions of one variable work. We know that this turning point, the derivative will be 0 at that spot. And so if we want to find a minimum or a maximum, we'll find the derivative and we'll set it to 0. And that will tell us where the minimum or maximum is. And we also know about second derivatives, which tell you about curvature. The second derivative of this is constant and tells us that it's actually curving generally upwards. So we know about all of those things. What we want to do is we want to figure out what that means with multivariable functions. In particular with two variable functions. So a function of two variables might be f of x and y comes out to some sort of something like that. Okay? And the way this works is that there is whoa. Let's draw that better. There's an x and y axis down here on the table, if you like, and each value of x and y, so you get a point like here, which has a value for x and a value for y, and you sub both of those values into this formula, and it tells you how far up or down to go. All right? And at each point, you might go below. It tells you how far up or down to go to produce the function. And the function will produce a surface. Something like this one, maybe. Okay? I bring this so that I can show you. Apologies to all those listening on the screen. You can't see this, but you can always come to the Maths Learning Centre and investigate the things that are made of string. So this is what is produced when you do a particular two-variable function. This function is something like x squared minus y squared. And at each point down here we could draw an x-axis and a y-axis, and at every point in here somewhere, we could sub that x and that y into the formula and figure out how high up to go to produce this function. And together, all of that produces a surface. Now, you can do it in 3D and 4D as well, but you can't draw pictures of them because you need an extra dimension to do the function axis. So we had 2 dimensions for the x and y, and a 3rd dimension tells you where the surface is. All right, so this surface is a hyperbolic paraboloid, for those of you who are in Maths 1B and need to know the name of that shape. And each one has its own shape, okay? And we would like to know where to find the maximums and minimums and saddle points, like this point just here. And that's not as easy as we would like. But that's the basic idea. So we're going to do everything that we used to do with ordinary functions and do it on multivariable functions. So first, we're going to think about domains and ranges. So with ordinary functions, with one variable functions, or possibly something worse than that. With ordinary functions, the domain is the part of the x-axis that you're using to create the formula, to use in the formula. It's the ones that you're allowed to use. And you're obviously not allowed to use anything that causes you to divide by 0. You're not allowed to put anything into ln that is negative. And all of those sorts of things are how you define the domain. And so we would say the domain of f is, well, I suppose the set of x's where x is not equal to 2. Because that's the place where it's not defined. We can't do it when x is 2 because it causes me to divide by 0. Right? Cool. And with one variable functions, we would always write the domain as an interval if we could, because it was a piece of the x-axis. And the range is all of the values that you could produce that came out of your function. So I really don't want to do it for this one. So I don't like it. But what we do to find a range is we would think about the values that can come out. So we'd say, can we produce 0? And the answer is yes, we can, I think, as long as you pick the right number that makes this top 0, which I think it actually has one, hopefully. I could be wrong. Can we produce 0? Is there a minimum that we can produce? Is there a maximum that we can produce? Can we produce positive numbers? Can we produce negative numbers? Can we produce as small a numbers as we like? Think through all of those options and possibly try and graph it somewhere and just look at the graph and go, ta-da, that's the range. And the graph would be with part of the y-axis that you covered. So the y values that come out. So we're used to that, and we did that quite a bit in first semester. We want to do it with multivariable functions. So with multivariable functions, it gets a bit harder because the domain is the set of x's and y's that are possible to produce an outcome. So over here, my domain is this square on the bottom. But technically, I suppose it could go on forever if I wanted. It may be that I'm only allowed to use x's and y's that are within a particular circle or something. I might have to draw a particular shape there, and that shape there, I'm only allowed to use the points in there as my x's and y's. I have to find combinations of x and y that are allowed. So the domain is the set of x and y that make the function defined. And it usually can't be said in any particularly useful way. See, in this one we can say x isn't 2, and that's fairly simple. Or we could say all the x is greater than 1, and that's fairly simple. But we have to have combinations of x and y, and they might have to be combined in a particular sort of way in order to work at all. So one of the classics is x and y. Just let me look up an assignment. Yep. Is that one. So that's a perfectly good function. If I pick most x's and y's, I can put them in and it will produce an answer. Okay? It'll sort of be a dome shape, this thing here. And I want to know for which combinations of x and y am I allowed to calculate this formula. And the only way of figuring it out is to have a look at the things that are involved. It's the square root of all of this stuff. And I can't do square root if it's negative, and draw a graph as well. So the domain, let's go back a bit. F is defined when 4 minus x squared minus y squared is positive, or 0. That's just saying, well, this number here, whatever it is, it can be 0. I'm allowed to do the square root of 0, but it can't be negative. So they're my possibilities. That's lovely. So the domain is the set of x's and y's that have that as a possibility. But what you want to do is rearrange it in such a way that it looks pretty and you can tell what it means. Because technically this should describe a region in the xy plane, and only when you're inside that region are you allowed to calculate the answer. So I might put the x squared and the y squared over here. And do that. The reason the lecturers have chosen this in this assignment is that they hope that you realise that this is the equation of a circle of radius 2 if it was equals. So 2 squared is 4. So x squared plus y squared is r squared is a circle. And because it's less than or equal to, it's the inside of a circle. And that circle is centred at the origin because it's just x squared plus y squared. So my domain of f, when I write it on page, it's the set of x's and y's such that x squared plus y squared is less than or equal to 4. There's no other way to describe it. I just have to write it as that formula. But this formula here is much prettier than that formula and is most likely to be what's in the solutions of the person marking your exam. And therefore is what you should write, because they will find it easier to mark your exam. Not that they won't give you the marks if it's written this way, but you want to make your marker to be in a happy mood when you do your solutions. So this is what you would write, but you could draw it too. And that would be it. So the point is that if I go upwards, where my z-axis would be to find the value of my function, the surface that I'm drawing only exists above this circle. Everything out there is blank. There's no surface there. The surface is only inside this circle, and it actually is a dome that goes over the top of that circle, actually. That's what the surface looks like. Okay? So some domains are shockingly worse. There was one in an assignment which was the top right corner and the bottom left corner all except a hyperbola that was crossed out. It can be as bad as that. In general, in an exam, it's fairly simple. But they're all the places that you're allowed to calculate your function. That's what the domain is. The range is a different story. The range is the set of values produced by your function. And the values that are produced by your function live on the z-axis. So on this thing, presuming this is the z-axis here, my function's range, at least in this domain, goes from here to here. Because they're all the things that are produced. It's the amount of the z-axis that I've covered with my function. It doesn't go any further below than this. It doesn't go any further up than this. That's my range. Of course, if this function went on forever, the range would be the whole of the z-axis. Let's think about this function here. Root 4 minus x squared minus y squared. Well, we think, can we make 0? Yes. Yes, we can. If we choose x and y correctly, on the edge of my circle, I can make the answer under here 0, and then we will get root 0 as the answer. Okay? And root can only be a positive number. I can't have a negative number, so I can't make any negative numbers. So far I've wiped out everything below here. So this is our z-axis. There's 0. We can't make any of that. We can make 0. And can I make any positive number at all? Well, no, I can't, because this is always less than 4. This number here, always less than 4, because x squared and y squared are both positive, so it's 4 minus those, so it has to be less than 4. So the maximum possible value we could possibly produce is root 4, which is 2. Can't produce anything above that either. So my range of f is everything from 0 to 2. And it is written as an interval because it's actually on the z-axis. It's just a set of single numbers. I already dealt with the multivariable bit in the domain, and the outcome is still just a single number. There do exist functions that produced vectors as their answer, and in Maths 1b they're called linear transformations, which I'll talk about tomorrow. Okay. That's domains and ranges. I would recommend that you have a look at the solutions to any assignment that talks about domains and ranges and try to imagine how you would have come up with the answer that they give. Because the answer they give, they just write it down. So you need to think through, say, well, if I think through that list, can I make 0, can I make positive, can I make negative, is there a maximum, is there a minimum? If you think through those 5 things, you'll be able to find the range. So this was my list of things to try. Can I make 0? Can I make positive? Can I make negative? Is there a maximum? Is there a minimum? And are there any other values that I just have to leave out because they're strange? Because I can't make them. So if you think through that list, it will help you to find the range. Because there's no particular method for finding the range, you just have to sort of think about it. So. Right, as I've said in multiple seminars before, this sort of thing is really useful for learning maths and passing an exam. Thinking of ways to describe things to yourself that says, if I were faced with this problem, what should I do and in what order in order to figure out an answer? So if you can find a process for yourself, it'll be easier to do it. Rather than just thinking, I have to find the range, what do I do? You say, okay, I can at least think through this list and I'll get something. Okay. There's the first page. Right, so that's domains and ranges. Awesome. So, cool. We've got our functions now. We can't graph them. There are very few of them that you can imagine. You can use a computer to do 3D graphing. And if you're really clever about the way you ask Wolfram Alpha to do stuff, you can actually get it to draw 3D graphs. It just takes a bit of work. But that's fine, we could do that. I really wish we had holograms for teaching maths 1 first year maths, because we could draw holograms of 3D functions and it would be so awesome. But if I could make holograms, I would probably go and make computer games or something instead. So we won't go there. So that's domains and ranges. The most important thing we want to do with functions of multiple variables is to find maximums and minimums. And in Maths 1b we also find just the general slope at any particular point, but it's the maxima and minima that we're most interested in. And therefore, since in one variable calculus finding maximums and minimums requires you to do derivatives, we need to find some way of calculating a derivative for a multiple variable function. We need some way of, if I'm at a particular spot, knowing what the slope is at this point. And that is really not very easy to describe. But what we can do is say, well, what if we just went this way, parallel to the x-axis? What would the slope be there? And what if we just went this way, parallel to the y-axis? What would the slope be there? Almost as if I slice it down here and it produces... Let me see if I can do this. what's my function look like? Okay, so I've got this awful surface, right? And I want to slice it in a particular direction. So I'm at a particular point, and I want to get my cutting plane and slice downwards to produce something like that. Okay, that's what I get when I slice my surface. And I want to know, here I am at that spot, what is the slope in this direction? Okay, I should have brought my Play-Doh, unfortunately. Just like if you've got a dome, you want to slice it this way and you make a lovely circle. So as another example, I might have a dome like that. And I might want to say, here I am at this point on the front. Well, I'll slice it here like that with my plane. And it will produce a curve like that. And I want to know, here I am at that point, what is the actual slope in that direction? I can at least do it in the x direction and the y direction. And that's what we mean by df on dx and df on dy. It's the slope looking a lot parallel to each of the axes and see, well, how does it slope away from me in that direction? I'm going to restrict my entire universe just to this plane that I'm standing in and look that way and see what the slope is there. Okay? So if that still freaks you out, I apologise. Come and talk to me in the Maths Learning Centre. But also you can actually do the calculations without understanding it, which I never recommend. But sometimes the calculations help you understand what's going on. Okay, so that was partial derivatives. So partial derivatives, the concept is that I've got my slice function parallel to, say, the x-axis and find the slope of the curve in that slice. So the point being that this whole function has a formula, but if I'm just looking in this slice, the y value is the same all the way in this slice because it lines up with a particular y on the y-axis down. That's the y-axis here. It's a z-axis upwards. That's the y-axis here. It lines up with particular value y. So in this slice here, every value of y is the same. And every point in here can be found by where its x-coordinate is. So I can create a formula for this slice just in terms of x as long as I know what y is. And then I can differentiate that formula and produce an answer. Okay? Now I'm not going to go through that. I would really like to hope that your lecturer talked that through and gave you an example where you said, y is 2, what's the... No, I'll just do it. Let's just do that one because it's awful. Okay. So if I pick a particular value of y and make a slice along that plane, so suppose choose y equals, say, 2, then, that's f of x, y, sorry. Then we have f of x2 is actually x times 2 squared minus 2 e to the x plus x minus 1. So we've got 4x minus 2 e to the x. It's actually 5x then, isn't it? Minus 1. And I have a perfectly good formula that only involves x. It doesn't involve y because I've picked y to be equal to... I've picked y to be actually equal to 2. So now that I'm just looking in that slice where y is equal to 2, it's just an ordinary function. It's an ordinary one-variable function, and I can find the derivative here. Just go out just a tiny bit. Just far enough to fit the whole page in. All right. So I could, therefore, now do a straight one. I could do that, which would give me 5 minus 2 e to the x. And that's the derivative. Yep. Oh, because there's 4 here and there's another one here. Yeah. Yeah. I only found that out before and didn't tell you. So that's the derivative of this function, which is a function, good old ordinary function of just y, of just z in terms of x. That's a 2, by the way. Okay? This is what we mean by the derivative of f in terms of x. Because what we do is we choose y to be any number we want and we figure it out. Okay? But we don't want to have to pick what y is. We want to say, well, if we chose y to be a constant, but we didn't actually know which value we chose, we could still figure this out. Because we could just treat y in this original formula as if it was a constant and see what happened then. That's the idea behind doing partial derivatives. Okay? Right. And so I could, for example, figure out, therefore, the slope in the x direction at the point, say, 5, 2, just as a random point, would of course be so y is 2. I sub the 2 in. I can do the derivative straight, and so it would just be this, which would be whatever it is. Okay? That is a way of doing it if you can't remember. But this is not going to work if you're going to do this course, because you keep being asked to do partial derivatives all the time. So we don't want to go there. But that's how it would work. So do not do it this way. However, if you did do that, they probably would still give you the marks. If all you wanted to do was find out what the slope is in the x direction at 0.52. But there's a better way. The better way is to say, well, actually, we'll call it z. When we say this, dz on dx, we mean that we're doing this process. We're choosing y to be constant. We're figuring out what the derivative is if y was a constant in terms of x, and that's the formula we get. It still has y's in it because we want to know what would have happened if we chose various different values for y. So we need to be able to put the y into the formula as well. But the concept is that we pretend y is a constant. So y squared is just a perfectly ordinary number. It could be 4, like it was up here. And so that's actually y squared x. If I was differentiating 4x, I would just end up with the 4. So it's y squared. That y is a constant. So when I differentiate, the constant multiplied will stay there, and I'll differentiate the e to the x, and it's that. And I'll differentiate the x, which will be 1, and I'll differentiate the minus 1, and it'll be 0. That's dz on dx. If you want to do it with f's, you can also write it as it's also equal to fx xy. It's the same thing. Okay, to say I had my original function and I differentiated it with respect to x. You can also do dz on dy. So this time I'm thinking I'm going to pick a particular value of x and put my plane the other way around and slice it this way instead of that way and figure out what the slope is in that direction. So in this case, let's see, the x is a constant and it's being multiplied on, so when I differentiate it will still be there. The derivative of y squared is 2y. The e to the x is a constant because it involves x. There's no y's here. This is just a number. So that will just be minus e to the x because it might as well just be minus 7y. This does not involve y, so it counts as a constant, so its derivative is 0, and the derivative of the minus 1 is also 0. So I get 2xy minus e to the x. Okay? So if I want to know what it is at a particular point, so at the point xy is equal to 5, 2, then I know that dz on, that was dz on dy, sorry. dz on dx would be y squared, so 2 squared minus 2 times e to the 5 plus 1, which is 5 minus 2e to the 5, exactly as we figured out before. And this is also denoted as fx at the point 5, 2. And fy at the point 5, 2, which is dz on dy, is, let's see, 2 times 5 times 2 minus e to the 5. Okay? And technically, you would probably figure out what this answer is, just so that you had a picture of how it worked. So what that means is in this function, I have no clue what these numbers are. They're both negative. So in this function, if I look in the x direction, look along the x-axis, it's sloping downwards that way. If I look in the y direction, it's sloping downwards that way away from me. Later on, directional derivatives in Maths 1b, you can choose any direction to look in and see whether it slopes up or down in that direction. Okay, cool. So, how are we going to find our maximums and minimums? Well, we find our maxima and minima by doing derivatives. So technically, at the top of a hill, it'll be flat in every direction you look. And in particular, it'll be flat in the x direction and in the y direction as well. Because at the very top of your hill, here, if I look in the x direction, it's the top of a tangent like that. If I look in the y direction, it's a flat tangent as well. So what you need is, in one variable calculus, let's put a heading. So in one variable calculus, then your max or min happen when dy on dx is 0. Okay, so you set dy on dx equals 0, you solve it, it tells you what x is, and you sub it back into the original function to figure out what the maximum or minimum is. Or they happen at the places at the edges. Okay? In two variable calculus, the maximum or minimum happen when both dz on dx and dz on dy are both 0 at the same time. Okay, if one of them is 0 but the other one's not, it doesn't count. They have to both be 0 at the same time. Now, as usual, it doesn't guarantee that it will be a maximum or a minimum, but it will tell you that a maximum minimum could happen there. So we want an example of that. And in three variable calculus, you need all three of the derivatives to be 0 at the same time. And in 4, you need all 4, and so on. So if I want to find the maximum and minimum of this, or whatever, if there are any, I need dz on dx. I've taken out the e to the x because I don't want it to be too hard for this particular one. I need dz on dy as well. Yep. Yes. So just checking. So with this one, if I'm doing with y, the x counts as a constant, so it will stay there and the derivative of y is 1. Okay, cool. And both of these have to be 0 at the same time in order to produce a maximum or a minimum. And, well, I'd be able to solve that because it doesn't involve x, and then sub it into the other one and figure out what x had to be. So the grand hope of this is if one of these two formulas doesn't involve x or y, then you can just solve it as you would an ordinary formula. So I know that y would be minus b plus or minus the square root of b squared minus 4ac. There aren't any solutions. Damn. That's negative. So no solutions. That was not as satisfying as I would have liked. That's okay. So this has no solutions, which means there are no maxima and minima. There are no places where the derivative in the x direction is 0 at all. So there can't be any because it's never 0. The x derivative is never 0. The y derivative is sometimes 0, but the x derivative isn't. All right. It would have been really nice if there was a solution. I'm very sorry about that. Okay, so let's see if I can make one up from an assignment maybe that actually has one. Just annoys me when this happens. I am right in that has no solutions, aren't I? Yeah, okay. Okay. Let me do this function here, which also doesn't have any maxima or minima. Maybe that one. Okay. So with this function, dz on dx is 2x, and the y disappears. dz on dy is 2y, because the x doesn't involve any y's. And both of them have to be 0 at the same time in order to produce a maximum or a minimum. And so this means that x has to be 0, and this means that y has to be 0. So the maximum or minimum occurs when, well, at the point 0, 0. That one's particularly simple. Sometimes what you have to do is get a solution for this and sub it into the other one. So let's see if I can make one that does that. Let me do that one. So this one, dz on dx, is, well, the y counts as a constant. All right? Oh, crap. Change the function. I want the one that's worthwhile. And dz on dy is 2xy. Okay? So in order to find a maximum or a minimum, they both have to be 0 at the same time. Because the slope in the x direction has to be flat, and the slope in the y direction has to be flat. And this one I can solve. So y squared minus 1 is 0, which means that y squared is 1, which means that y is plus or minus 1. And I can sub that into the other one and see what I get. Let's give them numbers. Sub it into number 2. So I've got 2x times 1 is 0, which means that 2x is 0, which means that x is 0. Or I have 2x times minus 1 is 0, which means that minus 2x is 0, which means that x is 0. So what we have is we have the combinations maximum and minima can occur when x is 0 and y is 1, or when x is 0 and y is minus 1. I don't know whether they're maximums or minimums yet, because that's a different story, but I can find where they are. So you need to combine all the options for y and which x's they go with, or vice versa, to see if you can find them. And there have been assignment questions where there are infinitely many, but generally they don't do that to you in an exam. So, yeah. Right. So the next question is, how do you tell if it's a maximum or a minimum? Because, I mean, we used to be able to do a sign diagram, right, for the slope. And that's so not going to work in multiple dimensions, because you've got your point here where you think it might be a maximum or a minimum, and you have to go all the way around, and you've got this sort of sign zone. And we're not going to go there. We actually need something else. In one variable calculus, we used to do the second derivative test. And if the second derivative was positive, it would tell us that it was generally curving up, and so it was a minimum. And if the second derivative was negative, it would be generally curving down, and that would be a maximum. So we want something like that as well. So let's go there. You do the second derivative test, don't you, in AQMF? Good. All right. So is it a maximum or a minimum? Because let's just see where we've been. We've figured out, we know how ranges, well, we're used to the concept of being asked about ranges and domains in ordinary functions, and we're now used to how it works in two variables. We know how to find derivatives in two variables now, and the next step is to figure out how to tell whether something's a maximum or a minimum or not. So now we need second derivatives, because we need a second derivative test, right? Problem is, second derivatives are a bit harder in multiple dimensions, because you can differentiate twice, sure, but you could differentiate with x and then differentiate with y, and you could differentiate with y and then differentiate with x. You could do x twice and y twice, so there's actually 4 options. And the second derivative test uses all 4. So just in terms of creating derivatives, we can get our original function, and we can differentiate with respect to x. And we can differentiate it with respect to y. We can differentiate with respect to x again. We can differentiate it with respect to y again, to y from here. And we can differentiate this with respect to x. And we can differentiate this with respect to y. So let me draw my picture heaps better than that. So if we differentiate with respect to x, we'll get, the dz on dx. If you differentiate with respect to y, you'll get dz on dy. If you differentiate with respect to x again, you'll get dz on dx, d on dx of that, so dx squared. If you differentiate with respect to y from here, it will actually be dz, d squared z on dy dx. If you differentiate with respect to x from here, it will be d squared z on dx dy. And if you differentiate with respect to y from here, it will be d squared z on dy squared. Sorry about that, it's a shocking diagram. It's much better when it's bigger. Alternatively, to draw it again with the f's, if we had f, we could differentiate with respect to x and get fx. We could differentiate with respect to y and get fy. We could differentiate with respect to x again and get fxx. We could differentiate with respect to y from here and get fxy. We could differentiate with respect to x from here and get fyx. And we can differentiate with respect to y from here and get fyy. I put an equals here because if your function is a decent function that you would care about, these will come out to the same answer anyway. So you only actually have to do one of them. But sometimes they ask you to do them both and confirm that they actually are the same. Okay? I should point out that technically, when you're doing the x version, the x and the y are in the opposite order than if you're doing the d version, but no one will notice, so don't worry about it. But they are in the opposite order because of the way that you think about how you write this thing. So let's actually do an example. All right. I want a really good one that actually works. So I'm going to go to your lecture notes. Right. So f of xy is x squared minus 12xy plus 8y cubed. Let's do that one. So in order to find and classify the extrema of, that's how the words go. So you find the places where it could be a maximum or a minimum, and you say whether they are maxima and minima. First I need to find the first derivatives and the second derivatives. So I need fx. So that with respect to x is 2x. That with respect to x, both the minus 12 and the y are constants, so it's minus 12y. That doesn't involve any x's, so it's a constant, so when I differentiate with respect to x, it will disappear. Okay, fy. So this with respect to y is 0, because it doesn't involve y. Both the minus 12 and the x are constants, so we'll get minus 12x. This doesn't involve any x's, so we can just do it as we want. So we get that for fx and fy. Awesome. So, to do fxx, I differentiate this one again with respect to x. So the derivative of this with respect to x is 2, and the derivative of this with respect to x is 0. Awesome. To get fxy, I differentiate this x with respect to y, and so that doesn't involve y, so it disappears, and that will be minus 12. I could just as easily have gone yx, and if I differentiate this with respect to, oh, that's a y. If I differentiate this with respect to x, I get minus 12, so I get the same answer for both. Okay, so fyy, that doesn't involve any y, so it'll disappear, and this would be 48y. Awesome. So there we have all of our first and second derivatives. Great. This is telling me that in the x direction, the curvature is 2. So this tells me that in the x direction, the slope is 2x minus whatever 12y is. And this is telling me that in that x direction, the curvature is 2, which means it's curving upwards. Okay? At every point, anywhere, it always curves up in the x direction. This tells me nothing happy. And this is telling me that in the y direction, it curves at 48y. So if y is negative, it's curving down, and if y is positive, it's curving up. That's what this is telling me. So over here, where y is negative, it's doing like this, and it will flatten out, and then it will start to go the other way. That's what it will look like. So it will be sort of a bowl that comes down and then goes the other way. So now we need to find our maxima and minima. So for max and min, we need fx to be 0 and fy to be 0. So we've got 2x minus 12y has to be 0, and minus 12x plus 24y squared has to be 0. So I need to solve those equations simultaneously, which I do not like, but that's okay. So this one, I can at least write x in terms of y, or y in terms of x, and sub it into here. So let's see. 2x equals 12y, x is equal to 6y. So I could sub x equals 6y into this formula, and it would tell me what y needed to be. So sub into number 2. So I get minus 12 times 6y plus 24y squared is equal to 0. Divide everything by 12. Divide everything by 2. So I've got y outside of minus 3 plus y. So that means that y is in fact either 0 or 3 in order to make that 0. Okay, so the process is usually to try and eliminate one of them and solve just for that. So now that y is 0 or 3, we know that if y is equal to 0, we want to sub that back in here. So we've got x is equal, so if y is equal to 0, that means x is equal to 6 times 0, which is 0. And if y is equal to 3, that means that x is 6 times 3, which is 18. So I now have the maxima and minima occur when xy is equal to either 0, 0, 0, 0, or 18, 3. Ta-da! Yay! So I have two places where it's either a maximum or a minimum or neither. And in order to figure out whether they're maxima or minima, I need to use the second derivative test, which requires me to calculate a little matrix, which has a name, the discriminant. So I need to do the discriminant. So the discriminant is the determinant of this matrix. It's got the xx and the yy on the diagonal, and the xy and the yx on the other diagonal. And if I find the determinant of that matrix, whether it's positive or negative will tell me whether will tell me whether it's a maximum or a minimum. But it's not nearly as easy as that. Never is. So they call this delta usually, which is Greek D. So let's see. This means that what I need to do is find the maximum, find what fxx and xy are at both of these points. So let's do it one at a time. If x is equal to 0, xy is equal to 0, 0, then we get that fxx, according to my formula, is 2. It's always 2. And fxy is minus 12, because it's always minus 12. And fyy is 48 times 0, which is 0. Okay? So I sub my point 0, 0 into these three formulas here to find out what those answers are. So my discriminant is therefore 2 minus 12, 0, 0, which is 2 times minus 12. Minus 48. What does that tell me? My lecture notes say that if I look closely enough at that, it says that what I have is a saddle point. Have I done that right? No, I have not. Thank you. You see, you're supposed to tell me this sort of thing. Is that better? Awesome. So, 2 times 0 minus 12 times minus 12, which is still negative, right? Is that okay? Only worse. Yep. It's negative 144. So it's negative, and my notes tell me that that actually means it's a saddle point. This here is a saddle point. Saddle point means that in one direction, it's the bottom, and in a different direction, it's the top. High enough, you can see that it goes that way over here. So in one direction, it's the minimum, in the other direction, it's the maximum, so it doesn't make any sense. It's a saddle point. Which means it's neither a maximum nor a minimum, because it's the bottom in one direction and the top in the other, so you really should ignore it. Okay, awesome. And then let's do the other point, and really hopefully it doesn't come out to a saddle point as well. So when xy is equal to 18.3, really? It's 144. Okay. So I subbed my point into all three of those formulas. These two are easy because they don't involve x and y. And now I need the discriminant again. And this time, the answer comes out to which is plus 144. So discriminant's positive this time. So when the discriminant's positive, my little book of notes says there's two options for what could happen. This is either going to be a minimum or a maximum. It'll be one of those two. It's definitely not a saddle point, but we don't know which one. But we do know which one because you know that it's either at the bottom of a valley or it's at the top of a hill. If it's at the top of a hill, the curvature in every direction must be negative. And if it was at the bottom of the valley, the curvature, no matter which way you look, must be positive because it's always curving up everywhere. So I just have to look in either the x direction or the y direction and see what the curvature is there. And look, curvature in the y direction is positive, in the x direction is positive. It must be a minimum. So therefore, it's a minimum at 18.3. If that had been negative, in fact they would have both had to have been negative, it would have been a maximum. If one of them was 0, if one of these two numbers was 0, then you just pick whichever one isn't 0. If they're both 0, then it would have been a saddle point anyway. So, yeah. So there you go. There's only one. So what have we got here? So we calculate the discriminant, and it either comes out as positive or negative. If it comes out as negative or 0, if it comes out as that's a saddle point, and this tells you nothing. So they won't give you that. And if they do, you'll say, we do not know. Because they haven't given you any other way of telling whether it's a maximum or a minimum. If it comes out as positive, then there's still two options. You look at fxx or possibly fxy. If it comes out as positive, then it means that in the x direction it's curving up like that, so it must be a minimum. And if it comes out as negative in the x direction, it's curving down like that, so it must be a maximum. There you go. That's it for AQMF. I felt like I was going fast, and I apologise. But there you go. So if you're in AQMF, feel free to go. The rest of you in 1B, in Maths 1B, I still want to talk about directional derivatives. So how are we doing? Yeah, I'm recording it though. Okay. No, I don't think so. Because no, I don't even know what fxy means. Someone's just said, is there any significance to fxy being negative? And my answer is I don't even know what fx means physically, because you've restricted it to the x direction and then you've differentiated in the y direction. It doesn't even make any sense. So no clue what that even means. And fxy, because fxy and fyx are the same, in that determinant you'll always end up with a minus a positive number there because they'll either both be positive or both be negative. So yeah, it doesn't mean anything, I don't think. I actually don't know what it means. I know what fxx means. Curvature in the x direction. Okay, awesome. So, you guys, AQMF, a different course for finance, they don't do directional derivatives, but they do something else. They do Lagrange multipliers, which is much more fun than directional derivatives. Right, here we go. What have we done so far? Let's just think about what we've done so far. So we've figured out domain and range. We've figured out how to do derivatives. sort of, at least in the x direction and the y. At least in the x direction and the y direction. We've figured out how to find maximas and minimums. And we've got a second derivative sort of test. And those things go together. So they are all things other than the x and y. These are all things that we used to be able to do with ordinary functions. Okay, while we're talking about derivatives, I will talk about directional derivatives. Because so far, all we've actually done is find a derivative in a certain direction. But if you're sitting on a surface, you may want to know that if you're sitting here, say, that if you go that way, sure, it's sloping down. If I go that way, it's sloping down. If I go this way, it's sloping up. If I go sort of straight that way, I'll be sloping down. If I pick the right direction, it will just be flat across here. So I need to know what the slope is in every direction, not just in the x direction and the y direction. And that's what directional derivatives are for. So what I do is really hard to do on the screen, so I apologize for everyone who's watching. I actually need to think about my direction in terms of a bird's eye view. Think about yourself as an orienteer or some sort of geologist or something who's standing on this in this gully here, and thinking about, in terms of their GPS system, what direction they're supposed to go in a north, south, east, west sort of direction. And that completely ignores how high this hill here is. That's what we need to do. So when we talk about the direction in that directional derivative, it's from a bird's eye view in a north, south, east, west sort of way. Okay, but we're going to do it in coordinates, of course, because we're doing coordinate geometry here. But that's what we're thinking about. It's not talking about the direction down the hill. It's saying, well, if I head north, yes, if I head north, will I be going up or down the hill? So bird's eye view heading north, up or down? Bird's eye view heading south, up or down? And those sorts of questions. That's what we want to know. And in fact, how strongly up and how strongly down? And exactly which direction should I go in a bird's eye view in order to not go up or down, but just stay on the surface? Okay? That's the big question of directional derivatives. So we'll go back a little. And what direction should I go in order to produce the greatest possible slope? Okay? They are the big questions now. So we want to do these now in any direction. And I said earlier, just so that's on paper, direction is described from a bird's eye view. Okay? So the concept is the same though. You have a direction. So this is the order you do it. You choose your direction. Okay? With your bird's eye view. You slice your surface with a plane that goes in that direction. Okay, so we've got our hill. And we choose any direction, not just x or y, but just some other random direction, and we slice our surface. And then you take the positive axis as the direction you're pointing in. So it could be that plus is this way, or plus could be that way. It actually makes a difference. So it depends on which side of this plane you're looking at. So if you're looking at it from this side, then that would be the positive direction. But if I was looking at it from this side, then that would be the positive direction. So you need to actually draw your graph on that plane looking from a particular side. Okay? So you slice your surface, and we do our derivative of that function that you make. Okay? That's what you're trying to do. Okay, so this is our process. Of course, there's just a formula for it. You don't actually do this, but that's what you're imagining. Okay, so what you need to do is there isn't an x-axis drawn on this plane that you've cut it with. You actually have to draw that x-axis yourself using a unit vector. So what we actually do before we do the derivative of that curve is we mark out an x-axis using a unit vector. So a unit vector is 1 long, and so it will properly mark the axis with length of 1, and so it will work properly. It won't be all squished up or spread out as it's supposed to be. And then once we've marked out the x-axis using a unit vector, we want to write the curve in terms of that x-axis, and then we do the derivative. That is the perspective. If you wanted to come up with a directional derivative on your own, that's what you would need to do. Okay? I'm not going to show you how that's done, but that's the point of this. You get your surface, you pick a direction, you slice it there, you draw an x-axis in one direction or the other, you mark it out using the unit vector that describes that direction, you rewrite your curve in terms of how far you are away from the 0 along that axis, and once you've got that formula, you can differentiate it, and that will tell you the slope. Long process, right? But the derivative is actually fairly simple, the formula for it. You know, compared to that, see, if I tell you this, you go, wow, that's really hard. And then when you look at the formula you give me, oh, that's really easy now. So, but before, it just looked awful. Okay, so that means that there are several parts to how to calculate this. So let's do it as an example so you can see what's going on. I'm just going to do one. Let's do the one I did before. Okay, so that function, don't know what it looks like, but that function there, I want to be at a particular point and figure out the directional derivative in a particular direction. So at the point minus 1, 1. So there's 3 pieces of information here. There's a directional derivative of the function f in the direction of that vector at a point, at this point. So bird's eye view, we find the point minus 1, 1. From that point, we go in the direction of 1, 2, and that marks out our new x-axis. So this is the picture that we imagine. So there's our xy. Bird's eye view, the function is here somewhere. I just can't see it because it's a bird's eye view. We go to the point minus 1, 1, which is here. And we're going in the direction of 1, 2. So 1, 2. Okay? So that vector there is 1, 2. And that is marking out my new x-axis. Okay? And I slice my surface here, and I look at it from over here, and then we'll cut my surface in a particular curve, and I'll find the derivative of that curve. That's what I'm doing by doing this. But there's a formula for it. Okay. So first, I need to mark out this x-axis in units of 1, because currently the length of this vector is not 1. I need to mark it out in 1. Okay, so I need a unit vector. So that vector describes the direction, but I need a unit vector in that direction. So it'll be 1 on root. Okay, because the root 5 is the length of this vector here, I think. Yes. Okay. So it needs to point in the same direction. I'm not allowed to use minus 1, minus 2, because that goes the wrong way. So first I need a unit vector. I also need the derivatives of my function, the first derivatives. So fx would be y squared minus y plus 1. And fy is 2xy minus x.